be disappointed. That's so annoying. But you know, Florida's not, I don't think Florida's a two-party state where both parties have to consent to being recorded. I know California is.
I Googled it at one point and it is a two-party state.
Is it a two-party state? Oh. So that's why that little recording's there, to make sure everybody knows. So you're all being recorded, but I'm gonna spotlight my video. That way it won't switch to your faces every time one of you says something. Although, did anybody in NHS, the officers, did any of you guys watch the video? Because we started recording it early. And so there's a whole lot of us just prepping. It's not good. There's going to have to be some editing done before we just post it on Canvas. Okay, so here we go. Calculating the electric potential starts from our concept of work. And that's where we ended yesterday before our question, that the work done in moving a charge comes from an integral. Now, the electric potential is defined as the work per unit charge. So when we divide both sides by Q, we get what's known as the electric potential. And that means that the electric potential is just about the field. And more importantly, it's about moving a particle from one place in the field to the other. Now, that being said, that sounds not like such a big deal, but there's actually three different ways to state this. There is the electric potential, there's the electric potential difference, and then there's just saying voltage. The truth is, if this was AP Physics 1, they'd all be the same. But this isn't. This is E&M. These all mean something different. And so I want to be very clear about why they mean something different. First, voltage tends to be slang for the electric potential difference of a battery. We will talk about voltage in circuits. It doesn't apply to the electric potential in space. So this is generally specific to circuits. We tend to not describe it as the electric potential in space. The electric potential difference is just that, the change in potential between 2 points. Now, this part's important. Increasing potential means you're moving against the field. That doesn't mean you're gaining energy. It just means you're moving against the field. An increase in potential, you're moving against the field. Decrease in potential, you're moving with the field. This is how we can determine the direction of the field from the potential. However, the electric potential is a potential difference that assumes an initial potential of 0. This is a hard concept, but the electric potential has no relativity. It assumes a reference point of 0 potential. This is a hard concept for me to share with you. So let me talk a little bit about reference points when it comes to potentials and energy and gravity and all of that. When we've talked about energy in here with gravity, we've always had to talk about the idea that there was a reference level. Do you remember that discussion last year in AP Physics 1? That if you lift something up, it acquires energy. But that, what do we use as our reference? For example, there's lots of stuff in my room. Stuff on a table in front of you. Does the object on the table in front of you have potential energy? Generally, that's an ambiguous question. Max, does your notebook have potential energy? Joey, does your teacup have potential energy? So the question is, well, I don't know. I couldn't answer that question for you without you suggesting something more. For example, I don't think your notebook or your teacup has potential energy. It's on the surface it's likely to stay on. Now, if you perch it at the edge of the surface that it's on, and there's the possibility it could fall, well, then the concept of potential energy becomes useful in discussing that object, because there is the possibility of a change in position due to it falling, so that potential energy becomes relevant. Did anything about the object actually change, though, when you slid it towards the edge of the table? Well, no. It didn't really acquire any more energy. It just now is precarious and could fall. But if it did fall, it probably will only fall to the floor, not to the ground. We're on the second story, right? So will we talk about the potential energy relative to the ground? I mean, if I dug a big hole outside, do I have to now reassess the potential energy of everything in the room? We have these relative points. And the truth is, for gravity or gravitational potential energy, it's all very relative to whatever you want to have as your lowest position. So we talk about roller coaster questions, and we always say, well, we say that the car has energy when it's at the top of the lift hill because we know it's got a bottom of that track somewhere, a lowest point it will likely make it to, assuming no problems. Well, does that mean that the surface of the Earth is zero? Is that the zero for gravity? Well, unfortunately, no. It doesn't, because you can always have some manipulation of that relative height. Because of that, what we call zero for reference is elusive. The truth is, we have gravity all wrong in our heads. When it comes to energy, it's all wrong. We will have to redefine it in mechanics in the way that we're going to define it right now for electronics. Because if I have a point charge in space right now, there's a single point charge like this in space, it doesn't cost me any energy to put it there. There's no field until the first charge is there. So if there's no field in this space, I can move this around anywhere I want to put it. And it doesn't cost me any energy to move it because there's no field there now, except for the field this particle creates. So in the emptiness, without any particle there at all, there is no electric field. So moving this charge, I don't have to move against a field to get it there. But now that there's a charge there, if I want to bring another charge close to it, it's going to cost me energy. This charge has established a field in this space. So if I want to figure out the electric potential here, that's actually me finding out how much energy it would take to move a particle to there. So if I want to do that and state the electric potential, I need to find a point that has zero energy associated with the second charge. That's my point of reference. Where is that? Is it the surface of this charge? Is that where there'd be zero energy? And you all know the answer's got to be no. Because if I put another charge here, put one right here, if I put it right next to it, is there zero energy involved with that? Is that the 0 point? Where's zero? Where do I start? Where do I have a place? Is there a place in the universe where the object has no energy relative to this charge? And The only answer can be that I would have to start my original charge infinitely far away, someplace so far away that these two charges don't interact at all. And that's actually considered the reference point for the electric potential. The reference point for electric potential is a point infinitely far away, where there's no interaction between the charges. So that's how these three words are different. In gravity, we've been looking at just gravitational potential differences. That's all MGH has ever been. But today we have to define the idea that there is a true reference, a true place that we have to begin, and that's the place where the objects don't interact in any way. And that place will be infinitely far apart. So if I want to calculate the electric potential, I have to make sure that my starting point is a point of reference where there's no potential. I'm going to say interaction. Or perhaps a place where the field is zero. Okay, with that being said, we're going to calculate the electric potential at a location near an established point charge. So to do that, we're going to say, find the electric potential a distance r away from my point charge. The process of calculating the electric potential doesn't require that I actually even use a test charge. It just requires that I use this formula. This is the formula for electric potential. It's on the equation sheet. It's like having the formula for work. And I'm going to be posting your equation sheets now. At this point, you're probably going to want to have a copy of it. I will allow equation sheets to be on every test from this point forward. If you haven't already gone and gotten it, this year's did not change compared to last year's. They finally released this year's equation sheet. Generally, I don't try to give the equation sheet out until AP has approved the equation sheet for the year, and they've made no change to it, so it's the same as last year. To calculate the electric potential, you need to first have something about the field. We need the formula or the expression for the electric field due to my charge distribution. Since it's just a point charge, we know what that is, but that's where you start. So one, you need an expression for the electric field. For your charge distribution. For a point charge, we already have that. We know this is going to be Q over R squared times 1 over 4 pi epsilon naught. Next, this one's not as hard, but we have to determine what the appropriate variable is in dealing with the integral. That's dependent on your situation. But we have to determine what to use for ds. Now, this one's not particularly hard, but there are some nuances here that I think some of you might appreciate. First, and I just want to have a blank slate for this. I know that the electric field is kind of streaming away from this particle in all directions. So I kind of want to draw a bunch of these just so I can give a kind of the purview. So this represents, all these electric field lines. If I'm bringing a test charge in from far away and I'm trying to set it close to this charge, I'm working against these field lines, and the field's getting stronger and stronger as I get closer to the charge. Hold on. So when I deal with finding the integral, I have to understand that it's E dot ds, but this represents making changes to the location of the particle and its effect on the electric field at those places. So when I'm moving my particle, do I want to move it along a path that's like this to go from one place to another and calculating the electric field? And what we find ultimately is that the path that we take doesn't matter unless the electric potential is changing along that path. What I mean is, if I take a path like this, is the field changing as I travel along this path? No, I'm staying the same distance away from the charge, so the field's not changing. And more importantly, if I looked at a piece of this, like from here to here, this little change, well, while I'm there, the electric field is this way, and I'm traveling this way. And there's going to be a dot product here, and that's a 90-degree difference, isn't it? Which means moving in this direction doesn't actually contribute at all to a change in potential. The only part that actually contributes is if I'm moving directly against or with the field. That's really what the nature of the line integral is here, to ensure that I'm only taking into account changes in motion relative to the field. So this whole expression is about figuring out what's the best method of getting to my area of zero potential to my location near my object. And I think for this case, it would be traveling along a radial path, one that takes me from wherever I am infinitely far away directly to a point here. Any other deviations from that radial path won't contribute to the electric potential. So if you want the short version of that, instead of the long drawn out one, which was mostly for Max's sake, because I think Max would ask me questions about that later, is when you use DS, you choose a path that has the most direct change against the field. It's that simple. If you're trying to calculate the electric potential, you choose a path that has the most direct change moving against the field. So for all the different shapes we've talked about, that's not particularly hard. But in this case, what it means is I'm going to adjust by saying I'm going to travel along a radius. By traveling along a radius, I have taken care of my dot product by compensating for it. We won't always get this opportunity. Sometimes we'll really have to take into account that dot product, but we do in this case. As long as I travel towards a radius, I know that I'm traveling this way and the electric field is going that way. Now, this does do something, though. This does make me consider that I have a cosine of 180 degrees I'm going to have to take into account here, because I'm moving from very far away towards the front. I'm going against the field. So I will have a cosine of 180 degrees to deal with. Now, the third thing, I need to set my limits. I want my starting limit to be a place where the electric field is zero. So, starting limit, That's not always possible, but that's what we try for. A place where there's no interaction. And your final limit is your landing location, the point in question. We want to end a distance r away from the charge. So I want to calculate the electric potential going from infinity, where there's no interaction, to a point, a distance r away from my charge. And I'm going to travel along a radial path, which produces a product of cosine 180. So I have an expression. My expression has r in it, which is what I would expect. I'm taking the integral with respect to that r, and I'm going to multiply by a cosine of 180 to ensure that I know that I'm doing my change from far, far away to where I'm going to be moving against the field. This is how we will calculate the electric potential. Now, that's setting up the electric potential. And the likelihood of you having to do a calculation like this on the exam, pretty small. But the result of this is very important to me and will be very important to us as a class. So let's do the calculation now. And this next portion isn't physics, it's calculus. So you may or may not be able to follow all of this. I hope that you can. Cosine 180 just gives me -1. So I think we can all agree that all I have to do is put the negative out front. The next part, a little bit harder. This doesn't change, right? It's a constant. Because it's a constant, I don't have to make that part of my integration. So I'm going to pull that out front as well. This, also a constant. It's not going to change. That's the charge that's at the center. So I'm going to pull it out front. And what I'm left with is that. Now, not a big deal here, ultimately. In fact, this is a pretty easy integral, but we haven't done one like this before. So to help you guys, I'm just going to write this as r to the -2 power and tell you that we do all the same things we did before. It's still a polynomial. And we treat it like a polynomial, which means we'll find the antiderivative by adding 1 to the exponent and then dividing by the new exponent. That's my antiderivative. Now, I have limits, so I'll put in my limits. And I can't forget my constant. Are we doing okay so far? Okay. Well, the next thing I do is just for us here is I'm going to simplify this, and I think you all can agree that it's just -1 over r. So now I can apply my limits. Applying the limits just means to put both limits in there. So I'll have negative 1 over r minus negative 1 over infinity. Now, 1 over infinity is just 0. So in physics, we get this a lot. We don't actually have infinity, but if you go far enough away, the distance is so far that it might as well be 0 here. And my negatives will cancel out, and I'm going to get for my electric potential Q over 4 pi epsilon naught times r. Now, this result, the electric potential for a point charge, it's as important as the electric field for a point charge. And I want to impress upon you, we're going to use this a lot. But the only thing I have to really point out to you is that it has no vector qualities. It's 1 over r, and it's pretty easy to use now because once we have this, we can do this for any kind of charge distribution. And also, I will point out that we have this for any distance away from our charge. And note that the electric potential does go to 0 as r goes to infinity. So this will represent the electric potential for any point charge or any configuration of point charges. So let me go back to our picture. Where was that? There. This tells me that my electric potential is going to get stronger as I get closer to my charge. Now, I don't know if this makes sense to you, what I'm about to say or not, but what it also means is that the potential increases as I get closer. So we could have points on our way to our charge that represent equipotential lines, meaning the potential is the same anywhere along that line because I am the same distance away from my charge. This is the reference to the topography map from yesterday. Equipotential points are points in space that all have the same potential. Around a point charge, they're circles. And they're concentric circles as you approach your single point charge. It takes no energy to move along an equipotential line. It only takes energy to move from one potential line to the next potential line. But also, electric fields have to run perpendicular to equipotential lines. I'm going to say that again because that's our first lab, our first real lab. We're going to measure potentials to track fields. And we're going to do this tomorrow. So I'll say it again. Electric fields have to run perpendicular to equipotential lines. The field represents the direction you go to change the potential, and you're working against the field to go have those change in potentials. So around a point charge, we have equipotential surfaces that are all spheres or circles around our point charge. And the electric fields have to be perpendicular. Every once in a while, they give us a test that has a topography map on it. And you're asked to make some judgment about the electric fields in that area from an equipotential topography map. So, electric field from a point charge, Q over 4 pi epsilon naught times 1 over r squared in the direction of r. Electric potential from a point charge, Q over 4 pi epsilon naught times 1 over r. Okay? Now, these questions that have charges in them like this, the way they're asked on the test are almost always the same. When it comes to point charge problems, now that we have the electric potential from a point charge, we have all these kinds of questions that have to do with finding out how the electric potential behaves in certain situations, like this one. Point P is at the center of this square, and this is a square. What's the electric field at point P? 0. What's the electric potential at point P? Also 0. Do you see why that has to be true? Now, I won't say interesting. Here's different ways they'll mess with that. Electric field at P. Is there one? Electric field? Sure there is. This way. That's the direction of the electric field at P. It's got to be downwards, right? 2 negative charges at the bottom, 2 positive charges at the top. A point particle there would definitely experience a force downwards. So electric field is downwards. But what's the electric potential there? Still 0. I have 2 positive, 2 negatives. The electric potential doesn't have direction. So it is a straight algebraic sum. So switching those 2 particles create an electric field there, but never change the electric potential. Electric field. Is there one? If so, what direction? What's that? There's no field there. A point charge would be pushed equally in all directions, no field. Is there electric potential there? Yes. 4 positive particles means that there's definitely electric potential. It's going to take energy to get there. And this is the thing. The thing about knowing the electric potential is about knowing how much energy it takes to get a particle there. Go back to yesterday. Electric potential is work over the charge, which means what we're really talking about when we know the electric potential is how much work it would take to put a charge at that location. What's crazy is when we go back to the example we had just a minute ago, the electric potential there is 0. The electric field there is 0. It takes no energy to put a particle there. Whatever amount of work it would take to overcome this charge is compensated for by this charge, and therefore it would take no energy to put a particle at the center. And once that particle's there, because the electric field is 0, it would stay there. However, I switch these 2 particles. I put the charges back the way I changed them to. Oh, I had 2 positives here, right? And 2 negatives here. Still takes no energy to put a particle there, but if I put a particle there, will it stay there? No, it's going to experience a force downwards. Yeah, because there's an electric field there. You can see these problems on the test, right? You can see the multiple choices kind of writing themselves, can't you? Yes, sir.
I was just thinking, so let's say if like the electric field moves the point, would the electric potential change?
You're gonna have to say that one more time.
Okay, like if we're saying like if the field pushes the point charge away, then would the electric potential change?
If the electric field, well, when I actually put a particle there.
Yeah, I'm saying like let's say the particle was there and it moved.
Okay. The thing is, if I actually do put a particle here, if I put a charge here, I would be changing the electric potential at that point. Or I'd at least be changing the electric potential in the area around that point, and thus I would be affecting the field around that. But this particle's electric potential and this particle's contribution to the field can't push this particle around. Right? The field created by, let me just differentiate, bless you. The field created by capital Q can't affect capital Q. It does create a field, but it can't be pushed around by its own field. Does that make sense? So yes, the space is now different because that particle is there, but it would only be affected by the other 4 particles. It wouldn't be affected by its own field or its own potential. Oh, if I start moving P around, I didn't say the electric potential would be the same everywhere around.
Yeah, no, that's what's kind
of. Okay, yeah, if I decide to put point P here, electric potential is probably still 0 there because I'm still equidistant from these two charges and equidistant from these two charges. So I'd probably still have electric potential of 0, but I don't know that that's going to be ubiquitous every place around here. It probably won't be. Max?
So I understand like everything up until where you say what it takes to put the charge there. Physically or what?
Yeah, physically. The amount of work it would take, the amount of energy you would have to expend to put the particle there is what I mean by what it would take to put the particle there. You see, once we know the electric potential, we are calculating specifically something about that location. Now, potential is defined as the work moving through an electric field divided by the charge that you push through the field. So once I know something about the electric potential at that place, let's just go back to a simpler diagram. If I know the electric potential at this location, and I do, it's this, then what I also know is how much energy it would take to put a charge there.
Yeah. So that's simple when it's just one. But like if you have the 4 of them, you would have to move it through the charges.
I know. And what it's telling us is that even though I have 4 charges there is a pathway to that location that takes no energy. I don't know what that pathway is. I don't have to. I just know that the amount of work to get there will be 0. Now, ultimately what that's probably making this harder than it seems to be. You would probably have to push sometimes, but the particle will probably be pulled other times. So at times when you're pushing, you're losing energy, but time where it's being pulled, you could gain that energy back, is what it's saying. So there'll be positive and negative work on the trip to get to that location, but the net work would be 0 to get there. Does that make sense now? Is that better? Now, there probably is a path to get there, but you know, that would be 0, but you know, that'd be a harder deal to deal with. There's something else about this that I think is important that it's kind of being lost. And there is a fragility to this that I don't want to leave out. If I know, let's make this kind of more, less nuanced. If I have a charge here of 2 coulombs and I want the electric potential 5 meters away, we can get a less nuanced answer. We can get a numerical answer to this. And it would be, you know, 2 divided by 4 pi epsilon naught times 5. This would be the electric potential at that location. Do me a favor, give me a number for this. It's big, really big. So if you don't remember all the things, it's, you know, 2 divided by 4 times 3.14 times 8.85 times 10 to the negative 12 times 5. So just give me 2 decimal places and times 10 to the. You got it? Yeah, then I'll wait patiently.
3.60 times 10 to the 12.
So we got some conflicting answers here. I got 3.6 times 10 to the 12th from Joey. I've got 3.5 times 10 to the 9th from Xavier. You got the same thing as who?
Well, 5.9, but then it rounds up because 5.96. So
Yeah, but they say times 10 to the 9th, and you say times 10 to the... To the 9th? All right.
Oh yeah, it is to the 9th. I wrote 5 instead of 2 when I did the...
So the units here, as we talked before, is a volt, which is a joule per second. So this would be 3.6 times 10 to the 9th volts. Now, here's the thing. Now that I know how much the electric potential is at this point, how fast would a 1 Coulomb charge have to be fired from infinity to land there? So think about this for a moment. We have the electric potential at that point. If I tell you that some other place far away, I happen to have a 1 Coulomb charge and I want to fire it at that point. I want to get 5 meters away from this charge by throwing something as fast as I can to get there. How fast would I have to throw it? Now, that seems like a ridiculous question until you realize we know how much work it would take to get to that point. Work is all about energy. What I really know is how much energy it takes to get to that point. So if I want to get my 1 Coulomb charge to this point, it's going to take 1 Coulomb times 3.6 times 10 to the 9th, or 3.6 times 10 to the 9th joules of energy, which means I know exactly how fast I'd have to get it there. You see, we use this kind of calculation to figure out how fast, say, hydrogen atoms have to be moving in the sun. We know how close they have to get to each other for them to have a nuclear fusion reaction. Therefore, we know how fast they must be traveling for those collisions to take place. It's done with this kind of calculation. All right, well, that was fun for me. Don't know how fun it was for all of you. So I hope you all have a nice day today.